This presentation is delivered by the Stanford Center for Professional Development.
All right, big day today. We're going to do our final application of convolution. I suppose I shouldn't say final application of convolution because it is the kind of operation that comes up repeatedly throughout the course. But sort of as the last treatment of the kind of the areas we've been talking about, I want to talk about an application of convolution to the central limit theorem. And this is one of my favorite topics because it just is it's such an important result. And it's such, in some sense, a surprising application of convolution, and the result itself is just so, I don't know, has this air of mystery about it that it's I think it's a real treat to see these ideas play out. So I want to talk about convolution and the central limit theorem. I will describe this, but it actually takes a little while to set up. We have to develop the appropriate language to get a precise statement of what the result is, and then understand how we're going to approach it. But the central limit theorem is, I say, one of the cornerstones of probability, and it's not only very important from a theoretical point of view, from the development of probability, but it's extremely important from the practical point of view. It has to do with the ubiquity of the bell-shaped curve, or why is it that so many things are distributed according to a Gaussian. So the central limit theorem, which like all good things has a three-letter acronym that goes along with it, the CLT somehow explains explains the bell-shaped curve, the universal appearance of the bell-shaped curve, that is to say the Gaussian. In probability. And there is a quote actually on this. There's a quote that's often repeated in connection with the central limit theorem that I put in the notes, and I just wanted to read it to you. It's by G. Lippmann, who's a French physicist. He says something like, everyone believes in the normal approximation. The normal approximation is another word for the Gaussian approximation, or the bell-shaped curve. He says everyone believes in the normal approximation. The mathematicians because they think the experimenters because they think it is a mathematical theorem. The mathematicians because they think it is an experimental fact. It's got something for everyone. All right, everybody buys it. Everybody believes it. And today, you will know why it's true. All right, now what does it say? Well, again, it's going to take us a little while, a couple of iterations before we get to a precise statement. What it says, it says that most probabilities, I mean, this is sort of an informal way of putting it. Most probabilities, some kind of average, really, is the way of thinking about it. Some kind of average, in some kind of average sense, are calculated, or approximated at least, as if they were distributed, as if they were determined by a bell-shaped curve, by a Gaussian. All right. The key word here, as it turns out, in the precise understanding of this, is averaging. All right. In an average sense, or averaging many outcomes, or many outcomes contributing in an average sense to the final outcome, are distributed according to a Gaussian. All right. Now, the picture of this, so before I make that precise, the picture is something like this. If you have a Gaussian, we're going to be working with a number of standard Gaussians. In the past, we've used e to the minus pi x squared. We're going to use a different one that's scaled differently today. We've used e to the minus pi x squared as a standard Gaussian. And that has the advantage that it's equal to its own Fourier transform. For the central limit theorem, the normalization is to take more standard normalization is to take, say p of x equals 1 over the square root of 2 pi e to the minus x squared over 2. Okay. Now, that has the advantage. I'm going to be using a lot of terms today, by the way, that I'm not going to completely define. I hope you have read or will read the section on this so that you pick up some of the terminology that we're going to use, like standard deviation, mean, variance, probability distributions, etc. If we went over all of those things, I wouldn't be able to get to the really core ideas in a short enough amount of time, sorry to say. So I'm counting on you to really pick up some of the background here on your own. And I wouldn't be surprised if you'd seen a lot of these things before. Matter of fact, I'd be surprised if you hadn't seen a lot of these things before. So the reason why you take this as the standard Gaussian in this case is that it has mean 0, mean or expected value 0, and it has standard deviation or variance 1. Okay? And the way it comes up in calculating probability is, again, something that you have probably seen is the probability. The idea is that this is supposed to represent the distribution of all possible outcomes to a measurement, an experiment, or whatever. And the probability that a measurement lies within a certain range is given by the area under the curve. All right, so the probability that a measurement that some sort of experiment or a measurement is between two numbers, a and b, is given by the area under the curve, the integral from a to b of e to the minus, well, 1 over square root of 2 pi, e to the minus x squared over 2 dx. This has to be calculated numerically because you can't integrate directly e to the minus x squared, e to the minus x squared over 2. All right, it doesn't have a simple antiderivative. That's the area under the Gaussian. Now, there is a strong sense, I haven't gotten to a precise statement of the theorem, but even in the informal way we've been talking about it, there's a strong sense of the universality of the central limit theorem. It says that most probabilities somehow are calculated or approximated by a Gaussian, right? In the average sense, about most probabilities that you're likely to run across, most measurements that you're likely to run across, if you average them all out, you find that they're distributed like a bell-shaped curve. Now, why should that be the case? Where is this element of universality coming from? Well, let me give you some indication and actually show you why, not why yet, but at least give you some indication how convolution is coming into this by showing you a series of quite startling pictures, I think. So I'm going to show some slides, if I may, some drawings, if I may. And I may because I'm the teacher. Sorry, I should have warned you beforehand. Hello back there. But first, a song. All right. Okay. Okay. So here's our friend, the screen. And there is the rectangle function, z0, all the way up and over and down and over. Okay? This is actually an appropriate lecture for Halloween time because of what you see, because of what you will see. The rectangle function, all right. All this build-up for the lousy rectangle function, right? Boy, that is impressive. All right. Now, you know what happens when you convolve the rectangle function with itself. You get the triangle function. Matter of fact, we've talked about that a number of times. I've even showed that. I even asked you to do that in homework. And if you read this section, you've seen these pictures. But nevertheless, you have to see them in full glory. So there's the rectangle function convolved with itself. It looks like the triangle function. All right. Fine. And remember, that was already an indication. That was already interesting itself. That showed somehow that the convolution is some kind of smoothing or averaging operation. All right. That the convolution of the discontinuous function, the rectangle, with itself is continuous. It's smoother than the original function. Okay? Now let's look at the convolution of the rectangle with itself 3 times. It is smoother still, and it starts to look a little bell-shaped. All right? You start to get a characteristic shape there that starts to resemble, in your imagination, the Gaussian. All right? And if you take the rectangle convolved with itself. Now, I wouldn't ask you to do that. This is all calculated with MATLAB, of course. I wouldn't ask you to actually carry out the integration and try to do this calculation. That's hard. I mean, it's actually a piecewise defined curve, but it's getting smoother and it's getting more bell-shaped. And if you take the rectangle convolved with itself 4 times, you get something that is very decidedly bell-shaped. Okay? All right, now that's already, I think, kind of impressive. But after all, the rectangle is a pretty simple-looking function. All right? There's nothing much to it. What's really spooky is if you start with something very much unlike the rectangle function, a random just assortment of a random collection of measurements and start taking the convolution, a random function, and start taking the convolution, you're going to find similar results. So for example, here is, again from the book, from the notes, here's a random signal. Now what I mean by this is I just asked MATLAB to generate a bunch of random numbers in between, I think it's just in between 0 and 1, and then join them by straight lines. All right, so it just jumps around according to what the numbers are. All right, so that's a well-defined, it's a random function somehow in the interval and just jumps all the way around. But okay, you can take the convolution of this thing with itself. All right, and here's what you get. If you take the convolution of this with itself, I call it the function f, you get something that still jumps around, but it is now very much triangular, whereas the first one looked pretty random. All right, pretty scattered all over the place. This one, there's sort of a, it goes up, it goes back down again. Take the convolution 3 times. All right, and you get something that looks like that. Now, it's still jaggedy. All right, it still has a lot of bumps into it, but look at it. I mean, it's getting kind of bell-shaped and it's getting smoother. And if you take the convolution 4 times with itself, you get something that looks like that, just 4 times. Now again, you can't see it quite so much on the resolution of the screen, but if I get close enough to it, I still see some jaggedy edges, no doubt, but they're getting smoothed out, and again, the overall shape of the curve is becoming more and more Gaussian. Now, I don't know, but I mean, it's pretty spooky, and I don't think there's any other word for it. All right, I think something is really going on here that you just have to understand. I mean, it has to somehow be, it's just really spooky. Okay? All right, that's all I'll do. Thank you very much. You can raise the screen. Okay, back to live action. So I want to explain that, all right? The content, the mathematical content of the central limit theorem is to explain that spookiness and to explain that universality. That in the limit, as something or other, as convolution is repeated, or as we'll make the connection as an averaging is taken, as an average is taken over more and more measurements, the result converges to something that is distributed according to a Gaussian. All right, that's what we want to get to. All right, so here is the setup. And again, it involves a certain, unavoidably, if you want to give a precise statement, that means you have to have precise language that goes into it. And I apologize ahead of time, again, for not defining all these terms. They're talked about more carefully in the notes, but I did want to go under the assumption that you've seen these things so we can get to the central point and not talk too much about background. All right, so here's the setup. All right, the primitive notion here is a random variable and how it's distributed. Primitive notion. That is to say, the first thing you define in order to talk about all other things is a random variable. And how it's distributed. All right, now a random variable, let me break that a little bit more neatly. A random variable, and I owe this definition to Sam Savage, who's a friend of mine in management science and engineering. A random variable is a number you don't know yet. That means that it's an outcome of a certain measurement. You're going to perform an experiment, you're going to make your measurement, and then you're going to get a number, but you don't know what that number is until you run the experiment, so you somehow want to keep a placeholder for doing the experiment. All right? So you call the random variable, generally speaking, by an uppercase letter, and the actual measurement you take by the corresponding lowercase letter. This is like Fourier Transforms, but in reverse. All right? So you call the random variable x, and the measurement, that is the value of the random variable, little x. All right? So again, intuitively, you think of capital X as a number you don't know yet. It's like measure the length of a pin, measure the height of a person across an entire population, all right? Or measure or the random variable is height. The value of the random variable is the measurement of the height of a particular person, all right? So it's a number that you have to compute by running an experiment, by doing a trial. Now, what you're interested in is the distribution of measurements. And that's given by, or it's usually called, the probability density function or the distribution associated with x. So you're interested in how the measurements x are distributed. The fraction of them within a certain range, the fraction of them between 1 and 2, the fraction of them between 2 and 3, and so on and so on. This is given by a function p of x, which is non-negative, or if I want to indicate the dependence on x, I may put a subscript in there. You know, piece of x, capital X. That is sometimes called the probability density function or the distribution function or whatever. All right. And it has the property that, not the property, but by definition, the probability that the measurement lies in a range between A and B is the integral of P between A and B, the area under the curve. So by definition, the probability that the measurements are going to take a value between A and B is the integral from A to B of P of x dx. Okay? So whatever shape the curve is in, whatever shape the curve has, it's positive. I compute the area under the curve from A to B, and that gives me the probability. Now, there's a special property of P, but only one, really two. One is that it's positive. The second is that the total area is 1. The measurement's got to be somewhere. So the probability that's between minus infinity and infinity is 1. So equals 1. Everybody got to be someplace, right? Every measurement's got to be somewhere. So that translates to a property of P, the integral from minus infinity to infinity of P of x dx is equal to 1. All right? So again, mathematical abstract treatments of this thing usually start by defining what you mean by a random variable, by defining what you mean by a density function. A density function is just defined by the properties. It's greater than or equal to 0, and its total integral is equal to 1, and then you define probability by this sort of integral. Okay, and again, these things are probably familiar to you, and I apologize for not really talking about them, talking about the background too much, but I do want to get to the punchline. All right, now, here is the key result. And here's how averaging starts to come into this. Averaging and really how convolutions start to come into this. Here's how averaging and convolution, I should say, are joined in this study. Okay? So here's the thing that gets it, that launches the whole, whole argument. The key result is suppose x1 and x2 are independent random variables. More on this in just a second. With distributions P, say 1 of x1 and P2 of x2. All right, so to say they're independent, that means that making a measurement of one doesn't affect the measurement of the other. All right, they're independent events. They don't have anything to do with each other. Okay, that's sort of intuitive way of saying it. But again, it's terminology that you have no doubt heard. But the idea again is there are numbers you don't know yet, and knowing one number doesn't affect knowing the other number. All right, so making a measurement of x1 doesn't affect making the measurement of x2, and vice versa. The question is, how is the sum distributed? And the answer is, by the convolution, it's distributed according to the convolution of the distributions of the separate random variables. That is, the distribution of x1 plus x2 is given by the convolution. P1 convolved with P2 of just P1 convolved with P2. I won't write the variable. All right? We'll bring averaging. Averaging doesn't come into this quite at this stage. Just think of this as the distribution of the sum is given by the convolution of the distributions. All right? Very impressive result. Very beautiful result. Now, let me show you how this goes. I'll get a proof of this for you. All right. The probability Here's the basic observation. The probability that x1 plus x2 for any, let me add one thing here. For any t, for any value of t, the probability that x1 plus x2 is less than or equal to t is given by this integral. Is given by a double integral. Over the region x1 plus x2, I'll draw a picture in just a second. X1 plus x2 less than or equal to t, p1 of x1 times p2 of x2 dx1 dx2. Now there's a certain amount to say here, a certain amount I will say and a certain amount that I won't say. All right, here is the region in the x1, x2 plane that I'm talking about. Here's x1, here's x2. The line x1 plus x2 equals t goes, say, like that. And we are interested in integrating under this region. Okay? Now, two things are happening here. You're making a measurement of x1, you're making a measurement of x2. You have a distribution for the random variable x1, you have a distribution for the random variable x2. Because they are independent, and this is where the assumption of independence comes in, to calculate the probability of something on both x1 and x2, to say that x1 plus x2 is less than or equal to t means the values of the sum lie underneath this line. You calculate the product, so it's like x1 is less than or equal to t. This is not quite right, but there's an and coming in here. Like x1 is less than or equal to t, and x2 is less than or equal to t. x1 plus x2 is less than or equal to t. I'm not saying this right. You calculate the integral of the product of the distributions of the two random variables separately over the region that you're talking about. And the region lies below the line x1 plus x2 equals t. All right? There's more of an argument for this, again, in the notes, but I just want to show you how the derivation goes once you accept this fact. And it's not so, if you think about this for a while, it's not an unreasonable statement. As a matter of fact, it's quite natural. All right, now, what I'm going to do is this integral, because the region is a little bit complicated, I can't, as I have before, uncouple this integral into two iterated single integrals, at least so easily, not the way it is written now. All right? The variables here are coupled in some sense because the region of integration is a little bit more complicated. It's not just a rectangle or something bounded by a horizontal or vertical line. But I can get to that picture if I make a change of variable in the integral. I want to work with this integral by making a change of variable, a relatively simple change of variable. I want to make a change of variable in the integral. Now, let me write down what it is, and then I'll explain what's going on here. The change of variable that I'm going to make is the variables are coupled. I'm going to let u equal x1, and I have to write this down because I want to get it right. V equals x1 plus x2. That defines u and v, my new variables, in terms of the old variables x1 and x2, or the old variables in terms of the new variables are x1 is equal to u and x2 is equal to v minus u. All right? So the line x1 plus x2 is equal to t is described in the other variables by x1 plus x2 is u plus v minus u is just v is described by v equals t. In other words, geometrically, the picture is this. Here is the x1, x2 plane. Here's the line x1 plus x2 equals t. And here's the region underneath it. Here is the uv plane over here. Here's the change of variables sort of that takes you from the uv plane to the x1, x2 plane. Here's the line v equals t. This region corresponds to this region under that change of variables. All right? And I'm going to make a corresponding, I have to carry that through and see what happens to the integral. And actually, there's a general theorem here that tells you how you make such a change of variables in a multiple integral, and I'm not going to go through that again. But in this case, it's particularly simple. It is something you may not have seen or may not be as familiar with as the ordinary integration by substitution that you've done many times. There's a little bit more involved in making a change of variable in a multiple integral. The so-called Jacobian of the transformation comes in. But as I like to say, if you're going to design transistors, chips with millions and millions of transistors on them, you can goddamn learn how to change variables in a double integral. I mean, it's not so hard. All right, it's not beyond your abilities. But nevertheless, I won't go through the formula. How does the change of variable work? Change the variables in the integral. In this case, it's particularly simple. You just get the integral over the region x1 plus x2 less than or equal to t, p1 of x1, p2 of x2, dx1, dx2 becomes the integral over, I have to describe the region, it's minus infinity, v is going from minus infinity up to t, u is going from minus infinity to plus infinity. And it is p1 of x1, x1 is u, p2 of x2, and x2 is v minus u. du dv. Okay? That's what it turns out to be. Now, do I have my order of integration right? I have my order of integration wrong here, I guess. Sorry. V is going from minus infinity up to t. U is going from minus infinity to infinity. All right, so dv du. Yeah, to describe the region in the uv plane, v is going from minus infinity up to t. U is going from minus infinity to infinity. All right, now I'm going to swap the order of integration. Let me leave that down there. I don't want to cut it off. So that's equal to the integral from minus infinity up to t. These are constants, all right? The limits of integration here are all constants, so it's easy just to swap the order of integration, something I could not have done so easily when the integral was written in terms of in the x1, x2 plane, all right? But because all the limits of integration are constant, it becomes easy to switch the order of integration. So integral from minus infinity to t, minus infinity to infinity, p1 of u, p2 of v minus u, du, and then the result is integrated with respect to v. All right, now there we are. We have eyes if only we but see. As you have heard me say before, what is inside the integral here? What is inside the inner integral? It's the integral of p1 of u times p2 of v minus u integrated with respect to u from minus infinity to infinity. That's just our friend, the convolution. That's the integral from minus infinity up to t of p1 convolved with p2 v or u du. Evaluated it. Sorry. I'll get it. Evaluated v, and then the results is integrated with respect to v. The inner integral is the convolution of p1 and p2 at v. Integral from minus infinity to infinity, p1 of u, p2 of v minus u du. Okay? Where do we start? Where do we finish? We see that the probability that x1 plus x2 is less than or equal to t is given by the integral from minus infinity up to t of p1 convolved with p2 v dv. All right, and that is enough to identify what you're integrating as the distribution for the probability of that random variable. And so this identifies this result, the fact that you get a probability by integrating, some function identifies this as the probability distribution. This identifies p1 convolved with p2 as the distribution of x1 plus x2. 2 exclamation points. It's really quite a striking result. And it's an extremely important result. Okay. Now, once again, this says that if you have two independent random variables, x1 and x2, so again, the measurement of one does not affect the measurement of the other. You ask the question, how is their sum distributed? The answer is their sum is distributed according to the convolution of the distribution of each one. All right, that's, in words, what we just showed here. And it's a very important, very fundamental result. It links the sum of random variables to convolution. It will link averages to convolution. All averages come as in a little bit later, in a matter of fact, in just a few moments. Now, also in the notes, you should take a look at, there's a discrete form of this, all right? As a matter of fact, I think I started off by motivating the more general result by looking at the discrete form, that is rolling a couple of dice, rolling one dice, rolling two dice, looking at the average, looking at the sum of two dice and so on. And you see exactly this result come in the discrete case. So if you're looking for a little bit more intuition about why convolution should come in when you're considering probabilities and sums, then look at the discrete case the way it's described there, because it also shows, I think, pretty convincingly why it is that a convolution should come in to describe the distribution of the sum. Okay, we are, however, dealing with it. We have to do everything in the continuous case. Simplify some things actually. All right, some of the calculations are actually simpler in the continuous case than in the discrete case, but it's a good motivation. All right, now I should say, by the way, that the result for two random variables also holds for a sum of any finite number of random variables. So you get a similar result for x1, x2. x1 plus x2 plus up to xn is distributed according to the convolution. According to the convolution. P1 star, P2 star, P3. All right, if you know the convolution of each, if they're independent, then you get then the sum is distributed according to the convolution of all of them. Same argument. I mean, you just work inductively. Okay, now with this, I can give the setup for the central limit theorem, the actual statement. All right, we're not quite there. We need a little bit more, a few more assumptions, which are natural, actually, which are the kind of assumptions that come up often when you're applying these sorts of ideas in practice and actually figuring out the distributions for actual measurements, actual experiments. So here's the setup for the CLT. So again, I have n random variables are n independent random variables. All right? Just as before, and eventually I'm going to let n tend to infinity here. I also assume that they have the same distribution. That the distributions are the same for all the xi's. Okay? That is, they're distributed in the same way. Now, that may seem like quite a strong assumption. It is in some sense, but it's also an assumption that is quite natural. That is, you're performing an experiment. If the measurements may be uniformly distributed, they're different sorts of measurements, but there's no reason to think they're distributed any other way. That making a measurement of one aspect of something, one aspect of an experiment is different or distributed differently from making a different measurement of the experiment. They all have the same distribution. And like anything else in this business that has an acronym associated with it, you say that x1 up to xn are IID. That stands for independent, identically distributed. I hate these things. Independent, identically distributed. But you see this terminology a lot, so you should know it. Now, let's call the distribution P, okay? Call the common distribution P. Then some further normalization is also possible. So let's call the distribution P of x. Okay, so it's the same distribution for each one of the random variables. Then you can normalize further. And again, this is explained in the notes. All right. You can assume that the mean of all the random, each one of the random variables is 0. You can assume mean 0. Mean 0. That is to, and that means that the integral from minus infinity to infinity of x times p of x dx is equal to 0. That's for all the random variables because they all have the same distribution. And you can assume, that's also called the expected value. And you can assume that the standard deviation, or variance, just the square of the standard deviation, is 1. I'm going to use the term standard deviation. I'm a little bit more used to that, actually. So I can assume standard deviation is 1. And that amounts to the assumption that the integral from minus infinity to infinity of x squared p of x, once the mean is equal to 0, then the assumption that the standard deviation is equal to 1 is this assumption. Okay? We already have another property of p, that the integral from minus infinity to infinity of p of x dx is equal to 1. The total area is equal to 1. P of x is positive, and the total area greater than or equal to 0, and the total area is equal to 1. We can further normalize to assume that the mean is 0, which means that the integral of x p of x dx is equal to 0, and the standard deviation is equal to 1, which means this integral x squared p of x is equal to 1. All right? Now, what is the distribution of the sum? That's what we want to get to. So what is the distribution xn? All right, well, now, that's actually, let me call this Sn, the sum of them. That's actually not quite what we want to look at because it doesn't have quite the same qualities as the separate random variables. All right, the mean of Sn is still 0, all right? But the standard deviation scales by the square root of n. But the standard deviation scales by the square root of n. That is to say, the standard deviation of just the sum is the square root of n. Of Sn is the square root of n. All right. We want the sum to be comparable to the separate random variables that are entering into it. So instead, we look at not just the sum, but this sum. Sn over the square root of n is x1 plus xn divided by the square root of n. That will have mean 0 and standard deviation 1. Mean 0, standard deviation 1. All right? Now, I can give you a statement of the central limit theorem. The statement of the central limit theorem says what happens to this average, this scaled average, Sn divided by square root of n as n tends to infinity. Says this. It says that the limit, there are different ways of stating it. One way of stating it is this. The limit is n tends to infinity of the probability that A is between, well, that the events you're measuring, the average of events, is between A and B, or should I say the scaled average of events is between A and B. The limit of that thing is n tends to infinity. As you take more and more measurements, or average more and more over a greater number of measurements, is the integral 1 over 2 pi, the integral from A to B of the corresponding Gaussian, which also has mean 0 and standard deviation 1. All right, so once again, this sum has mean 0 and standard deviation 1. All right, you take greater and greater, you take more and more measurements. You're averaging out a series of measurements over a whole bunch of experiments. how are your values distributed? What is the probability that your measurements are going to lie within a certain range as you take more and more measurements and average them all out? The answer is that in the limit, it's distributed according to a Gaussian. That probability is calculated as if you were calculating the probability based on a Gaussian. All right? So that means if n is pretty large, for example, you're probably getting a pretty good approximation if you assume that the scaled sum over there is distributed approximately according to a Gaussian. All right? What I'm going to show is, this is one version of the central limit theorem. I'm going to show an unintegrated form of that. Unintegrated form of this. Namely, if P of n of x is the distribution of that sum of x1 plus xn divided by the square root of n, then I'll show that P sub n itself tends to the Gaussian as n tends to infinity. Then P sub n of x tends to 1 over the square root of 2 pi e to the minus x squared over 2 as n tends to infinity. All right, if we know that, then the integrated form follows. Okay? All right. Now, looks like quite a complicated statement. We know what P sub n is, actually. P sub n is easy to write down. The distribution, well, one thing at a time here, one thing at a time. So once again, P of x is the distribution for x1, x2, up to xn. They all have the same distribution, all right? P convolve with itself n times. So that's P convolve with P n times of x. That's the distribution for the sum. That's the key result. It relates the sum to the convolution, is the distribution of x1 plus xn. But I don't have that exactly. I have the scaled version of that. And there's something a little extra that happens here. And again, I have to refer you to the notes for a derivation of this. Let me just write down what the result is. The distribution of x1 plus xn, if I scale it, is the square root of n times the n-fold convolution evaluated at the square root of n times x. So it actually scales both outside and inside the variable. All right, that's a fact. That's sort of a mathematical fact that comes from change of variables in scaling and how probability distributions behave under change of variables. So for that, I have to refer you to the notes. All right, so just take that on faith right now, or look it up. All right, so in other words, P sub n of x, that's the probability distribution of the scaled one, x1 plus xn, square root of n, is given by this formula, square root of n, the n-fold convolution of P with itself, evaluated at the square root of n times x. All right? Now, how the hell are you going to show that this n-fold convolution, or the scaled version of this n-fold convolution, tends to a Gaussian? All right? I mean, it doesn't look like I made the problem any simpler. I mean, convolution is given by a pretty complicated integral, and I have an n-fold kind. I don't have just a convolution of two functions. I have the convolution of n functions. And I want to take the limit of that thing as n tends to infinity. All right, the key to analyzing this is the Fourier transform, because the Fourier transform turns convolution into multiplication. Multiplication is easier to analyze than convolution. All right, I want to take the Fourier transform. I'll do it down here. The board gets too covered up. Take the Fourier transform. of that function, square root of n p convolve with itself n times. Evaluate the square root of n times x. Okay? All right, now, what do you get? And the idea is that multiplication, this turns convolution into multiplication into multiplication. Easier, we hope, to analyze. All right, now, how do we do it? Well, I apply the stretch theorem. The Fourier transform of Pn of x is the Fourier transform of this scaled convolution. So it is the square root of n, that comes out, of the Fourier transform of the n-fold convolution evaluated at the square root of n times x. Now remember, this is not each individual function evaluated. I have to be a little careful here. This is not each individual function evaluated at this is where you have to be careful about your variables. So let me try to get a sentence out here. It's not each individual function evaluated at the square root of n times x. It's the convolution evaluated at the square root of n times x. All right? So it's this Fourier transform of some big hairy function evaluated at the square root of n times x. This is the square root of n divided times 1 of the square root of n if I apply the shift theorem of the Fourier transform of p star n evaluated at s over the square root of n. All right, just applying the shift theorem. Now the Fourier transform of the convolution is the product of the Fourier transform It's an n-fold convolution, so I have the product of the Fourier transform of p with itself n times. So the square root of n here cancels with 1 of the square root of n there. This is the Fourier transform of p raised to the nth power evaluated at s over the square root of n. Okay? In other words, it's the Fourier another way of writing it. It's the Fourier transform of p evaluated at s over the square root of n raised to the nth power. Okay, make sure you follow the statement there. I mean, the one thing I didn't show you was why the distribution of the scaled average looked like this. But once you know this, then you can find its Fourier transform just by applying the shift theorem. And again, you have to be a little careful here. You have to realize it's the n-fold convolution evaluated at the square root of n times x. All right, not each individual function evaluated, not each individual term in the convolution evaluated there, but the whole convolution itself evaluated at the square root of n times x. Okay? Now. We are almost there, baby. Can you feel the excitement? I'm sure that you can. All right. The Fourier transform of p at s over the square root of n is equal to the integral from minus infinity to infinity. I have to write down the formula for the Fourier transform, believe it or not. E to the minus 2 pi I s over the square root of n x p of x dx. Okay? Now, of all things, I'm going to use the Taylor series, yes, for the complex exponential. This I think goes under the heading of dirty tricks. All right, this integral from minus infinity to infinity. What is the Taylor series of the complex exponential of any exponential? It's 1 minus 2 pi I s over the square root of n. Let me write s x over the square root of n. 1 plus x squared over 2 factorial plus x cubed over 3 factorial and so on and so on. So it's this term, 1, and then there's a minus sign here because it's e to the minus 2 pi s and x. Then the next term is squared, but there's an I there. And so this becomes minus 2 pi, let me just write it out here, 2 pi s x squared divided by square root of n. The whole thing squared, 1/2 of this, minus 1/2, there we go. I got it. Plus and so on and so on, plus small terms, higher order terms, times p of x. Check me here. So again, I just use e to the x, or e to the anything, e to the anything, e to the x, is 1 plus x squared over 2 factorial, plus and so on, all right? That's all I'm using. Okay, Now, watch this. Watch this. This is the integral from minus infinity to infinity, p of x minus, let me do this, dx minus, let me start to take out the terms here, minus the integral from minus infinity to infinity of their constants out here in front here, 2 pi I s, s comes out over the square root of n times the integral from minus infinity to infinity of x times p of x dx, all right? Minus, what's the next term here? 2 pi squared s squared x squared. So 2 pi squared, that's 4 pi squared s squared divided by 2 gives me a 2 pi squared s squared divided by n times the integral from minus infinity to infinity of x squared p of x dx plus other small terms, or terms that can be estimated. I will say not much more about them now, but I can give you some more details about that later. The important thing is just to keep the first couple of terms. So all I did here was multiply p of x through by the first couple of terms in the Taylor series, and then there's another integral of p of x times these higher order terms. Okay? Now, use the normalization. Integral of p of x is 1. All right? The integral of x times p of x, that's the mean, that's 0. All right? And the integral of x squared p of x is 1, because the variance, the standard deviation is 1. This integral is 1. What results from this dirty trick? What's left? What's left is 1 minus 2 pi squared s squared over n plus, let me just say, small or plus error terms. I'll just call them small. Okay? All right. What has happened here? We got to go, man. We have found that the Fourier transform of p at s over the square root of n is, let's say, approximately 1 minus 2 pi squared s squared divided by n. All right? That's the Fourier transform of the function p. We want the nth power of that, right? The Fourier transform of p s over the square root of n to the n, because that's the n-fold convolution that comes in, is this raised to the nth power. 1 minus 2 pi squared s squared divided by n to the nth power. Now you have to remember something from calculus. All right? This 1 minus 2 pi squared s squared over n to the n, 1 minus something over n to the nth power, as n tends to infinity, goes to an exponential. All right? This quantity to the nth power, as n tends to infinity, tends to an exponential. 1 minus 2 pi squared s squared over n to the n is approximately, and actually tends to in the limit, e to the minus 2 pi squared over s squared. 2 pi squared, yeah, over s squared. As n tends to infinity. Well, it's approximately this, and it gets better and better as n tends to infinity. Now you take the inverse Fourier transform. All right, the Fourier transform is tending of the convolution of the distribution is the distribution is tending to this thing as n is tending to infinity. I think it's okay. Take the inverse Fourier transform and you get the result. Because you know the Fourier transform of the Gaussian is the Gaussian, you know what to do with a scaled Gaussian by invoking the theorems, and you find, if I got it right, that the result of this is that the original function f sub n, p sub n, the Fourier distribution of the scaled average of the random variables tends to a Gaussian as n tends to infinity. It's unbelievable. All right, and that wraps it up. We brought that baby home only 5 minutes late. Okay, next time.